Hi, for this video I'm going to go over two practice problems that you would often see with chemical equilibrium. Calculating equilibrium concentrations, equilibrium partial pressures, calculating Kp, calculating Kc, and using an ice table to do that. So this is example 1 that I will go through. So you have a mixture of 0.2 moles of CO2, 0.1 moles of H2O, and 0.16 moles of H2O in a container initially. There's no CO initially in that container. So there's going to be 4 questions we answer here. First one, A, calculate the initial partial pressures of CO2, H2, and H2O. So for part A, how we're going to calculate the initial pressures, partial pressures for each of them is going to be using the ideal gas law. So PV equals nRT. Because the info we've got, we have the number of moles of each of the gases we have. And we have the volume, we have the temperature. So we have moles, volume, temperature. The only unknown is the pressure. So we can get the partial pressure of each of them. So it was 0.2 moles of CO2, 0.1 moles of H2, and then 0.16 moles of H2O. So rearranging the ideal gas law, we get P equals nRT over V. So the partial pressure of CO2 will equal the moles, so 0.2 moles times R, 0.0821 liter ATM per mole Kelvin, times temperature, which was 500 Kelvin, all over a volume of 2 liters, and this will give 4.105 ATM. So the partial pressure of H2 will be calculated in a similar manner. It's going to be 0.1 moles times 0.0821 liter ATM per mole Kelvin times 500 over 2 liters to give 2.053 ATM. And then the partial pressure of H2O is going to equal 0.16 moles times 0.0821 liter ATM per mole Kelvin times 500 Kelvin all over 2 liters. And this will give 3.284 ATM. So that is the answer for part A, the partial pressures of each of them initially. So then part B now. The information we're given for part B is that at equilibrium, the pressure of H2O is 3.51 ATM. So the pressure of H2O at equilibrium is equal to 3.51 ATM. And it's calculate the equilibrium pressures of the other 3 gases. So this is where the ice table is going to come in now. So what an ice table means, and I'll set it up here. So the equation, right, if we go back, first page, CO2 H2 CO and H2O. Those are the 4 compounds involved in this. The I stands for initial, C is change, and E is equilibrium. So the first row is going to be the initial partial pressures, each of them, which we solved in part A. So CO2, it's 4.105. For H2, it's 2.053. For CO, it was 0. And for H2O, it's 3.284. In the reaction, all of them have a coefficient of 1. So there's a 1-to-1 stoichiometric ratio between all of the reactants and the products. So for this change, we don't know how much pressure is being lost or being gained, so that's an unknown. So we're going to put in X as the unknown. The reactants are going to lose all an unknown amount, and the products will gain the unknown amount. The reason all of these are X is because they lose or they gain the same amount because their stoichiometric coefficients are the same. So that means at equilibrium, it's 4.105 minus X, 2.053 minus X, X, and we are told H2O's final is 3.51. So we can solve for X by saying, I'm going to put it in a different color, 3.284 plus X equals 3.51. So X is equal to 0.226 atmospheres. So then at equilibrium, the pressure of CO2, pressure of H2, pressure of CO, and pressure of H2O. So H2O we know is 3.51. CO, it's just equal to X, so 0.226. Then for CO2, it's going to be 4.105 minus X, which is 3.88. And then H2, it's 2.053 minus X, which winds up being 1.83. So those are the equilibrium partial pressures of all of the components of this reaction. Part C asks us to find Kp. So Kp equals the pressure of H2O times the pressure of CO, the products, over the pressure of CO2 times the pressure of H2, which are the reactants. So we go back, the top it's going to be 0.226. H2O is 3.51 over CO2, 3.88, and then 1.83 for H2. And sorry I have to keep going back between the screens, but this is a long problem and there's not enough room on each of these pages to complete the entire problem. So if I do the math here, to figure out Kp, just plugging in the equilibrium partial pressures that we got, and all of these exponents are just 1, since their coefficients are 1 in the reaction, I get a Kp of 0.12. Actually, no, it has no units, right? All the atmospheres cancel each other out, so it's just 0.112. So now Kc, if you remember the equation, Kc equals Kp times RT to the delta N. In this case, delta N is equal to 0 because there's 2 moles of product minus 2 moles of reactant. So this cancels out to 1, and Kc is equal to Kp, which is equal to 0.112. So that is the first sample problem where we are given a final equilibrium pressure. We're able to solve for the initial equilibrium pressures, and from there, we're able to calculate the Kp and the Kc. In example 2 here, we're given Kc, and we're given an initial concentration, but we're not given any final equilibrium concentrations. So we have to find those in a slightly different method than how we found the equilibrium concentrations last time, or partial pressures. Okay, I'm going to set up an ice table here again. So we got initial, change, and equilibrium. We're told initially that the concentration of H2O is 0.31 molar. And we have initial concentrations of 0 for the H2 and 0 for the O2. The change, though, because we have different coefficients now, you're going to lose minus 2x for H2O plus 2x for H2, and then plus x for O2. So your final 0.31 minus 2x, 2x, and x. Because I have Kc, I can plug into the equilibrium constant equation to solve for x. And I'll move over to the next page to do that. So the Kc, this Kc is going to equal the concentration of H2 squared times the concentration of O2 over the concentration of H2O squared. Kc is 4.12 times 10 to the minus 6th. H2 at equilibrium is 2x squared. The concentration of O is x. And then the concentration of H2O is 0.31 minus 2x. This would be a difficult equation to solve because it would end up being a quadratic equation. However, if you notice the Kc value, it's very tiny, meaning that the 0.31 number here is much larger than the numbers on top. So that means x has to be very tiny. Because x is so small, subtracting it from 0.31 doesn't really change the number at all. So we can ignore that minus 2x because it's not going to change this bottom number. It's going to be 0.31 minus a very small number, so we can eliminate that 2x. So now if I multiply each side by 0.31, I'll get 4x cubed is equal to 0.31 times 4.12 times 10 to the minus 6th. So I divide each side by 4. I get x cubed is equal to 1.227 times 10 to the minus 6th molar cubed. So then take the cube root of each of those, and x is equal to 0.011 molar. So, if I go back to this page X equals 0.011 molar, at equilibrium, the concentration of H2O is 0.30 molar, concentration of H2 is 0.022 molar, and the concentration of O2 is 0.011 molar. So that is how you solve a question where you're given a Kc value and an initial concentration, but you're not given any of the equilibrium concentrations. So I'll have 2 more videos on chemical equilibrium. The next one will be on reaction quotients, followed by Le Chatelier's principle.